I wanna talk about my presentation. My presentation is page replacement algorithm in operation system. Yeah, you can see my student number and my name. I wanna talk about introduction. In introduction is go introduction to virtual memory and page replacement. Modern operation systems rely heavily on virtual memory to allow programs to run even when they do not fully fit into physical RAM. Virtual memory creates an abstraction layer, giving each process the illusion of having its own larger, continuous memory space. This is made possible through paging, where memory is divided into fixed-size pages in the virtual address space and equal-sized frames in the physical memory. When a program accesses a page that is not currently loaded in RAM, the system generates a page fault. The operation system must then bring that page from the disk into a free frame. However, when memory is already full, the OS must choose a page to evict from RAM to make space. This choice is handled by page replacement algorithm, one of the most important components of memory management. A good algorithm reduces page fault and improves performance. A poor algorithm, however, may overload the system with page faults, leading to thrashing, a condition where the CPU spends most of its time swapping pages instead of exiting instructions. This presentation explores the most important replacement algorithm, how they work, and their strengths and weaknesses. In here, I want to talk virtual memory mechanics and performance metrics. In first is going to be paging hardware and page table. Every virtual page maps to a physical frame through the page table model. CPU include a TLB, translation lookaside buffer, to speed up this process. A TLB hit means fast memory access. A TLB miss means checking the page table and potentially a page fault. In second, page table entry bits. Wallet bit indicates if the page is in memory. Reference bit tracks recent page usage. Dirty bit M flags if the page has been modified requiring write back to disk. In third one, page fall rate. The primary performance metric number of the page falls divided by total memory accesses directly impacts effective access time EAT, as disk access is significantly slower than RAM. Even small increases in page falls directly slow down systems. In 4, it will be validly anomaly and working set. Validates anomaly seen in FIFO, where more frames increase false. LRU and optional avoid this. The working set model helps prevent the thrashing by ensuring process have enough pace for the currently locality of reference. And in here, classic page replacement algorithm. Optimal OPT evicts the page that won't be needed for the longest time in the future. Theoretically, it guarantees the minimum number of page faults. However, it's impossible to implement in real system as it requires predicting future page access, used as benchmark for compression. FIFO, first in first out, the simplest strategy, evicting the oldest page in memory. Easy to implement but ignores locality of reference, often removing frequently used pages. Suffer from Beladis anomaly, meaning performance can decrease with more memory. LRU, least recently used. based on temporal locality. It evicts the page that has not been used for the longest time. More effective than FIFO, True LRU is computationally expensive to implement due to the need for timestamps or constant linked list updates, making it impractical for most general purpose OSC. In practical, I will talk about practical and adaptive algorithm. Approximation of LRU. Since poor LRU is too costly, operation system use approximation, often leveraging hardware support like reference bits. NRU, not recently used, classifies page into four categories based on R referenced and M modified bits. Pages that haven't been referenced and are clean are prime candidates for eviction, simple yet effective when R bits are periodically cleared. Aging algorithm, a better LRU approximation using counters. Periodically, counters are shifted right, with the reference bit added to the most significant bit. This provides a more detailed history of page usage than a single R bit. Clock second chance, widely used in OS like Linux and Unix. Pages form a circular list. A pointer moves and the page with R equal 1 get second chance R bit cleared. Page with R equal 0 are evicted. And hence clock also considers the dirty bit to reduce disk writes. Adaptive algorithm. This algorithm addresses weaknesses like scan pollution, where a single large file read can evict frequently used pages. 2Q, LIRC, and LIRC identifies valuable pages by analyzing inter-references recency. ARC dynamically balances recurrent and frequency using ghost lists, making it highly effective in modern file systems like ZFS for device workloads. In conclusion, I will talk about modern trends. Evolving memory architectures. New non-volatile memory (NVM) blurs the lines between memory and storage. Future OS will manage multi-tier hierarchies: DRAM for hot page, NVM for warm, and disk for cold, necessitating new replacement strategies. Machine learning based algorithm emerging as research focus on ML to learn access patterns and predict page references, while computationally intensive and experimental. This direction promises smarter, more adaptive memory management for future computing. In conclusion, no single page replacement algorithm is perfect for all situations. Each has trade-offs, and the best choice depends on the specific workload and hardware capabilities. OPT provides theoretical best performance but is unimplementable. LRU models real behavior well but is too expensive to implement preciously. Clock offers an efficient compromise widely used on OS kernels. Adaptive algorithm RSC LIRS deliver excellent performance for modern workloads, especially those with large data scans or mixed locality. As the hardware and the workloads continue to evolve, page replacement algorithm must also adapt, ensuring efficient and reliable virtual memory management for future computing systems. Thank you for listening.